This is lab 4, Oscillations. In this lab, I had to analyze and model a spring mass system in which the mass moves in a two-dimensional oscillating motion. Other objectives of this lab included comparing the predicted and observed motion of the system and plotting energy changes associated with the system's motion. To do this, I used the momentum principle to calculate all forces acting on the system and to assist in predicting the system's motion. Additionally, I used the energy principle to calculate energy changes associated with the system, and after completing the lab, one of the key results was that the system's change in energy was zero due to it being a closed system. As stated earlier, I used the momentum and energy principle. From lecture, we learned that we can manipulate the momentum principle and use the update equations to predict the system's motion. Also, we use Hooke's law here since our system includes a spring. Additionally, we learned that the energy principle states that the change in energy is equal to the work done on the system by the surroundings, and it asserts that energy cannot be created nor destroyed. This principle is useful for this lab because it will help us analyze our multi-particle system and calculate its potential energies, whose formulas are shown below. The image to the left shows how potential energy arises from the interaction of a pair of objects, similar to the spring mass system in the lab. To the left, you can see the video I analyzed in Tracker. The system was the spring, mass, and the earth. The forces involved were the spring and gravitational forces, and the energy variation involved was the mass's kinetic energy and the spring and gravitational potential energies. Here I set the initial conditions in Tracker and calculated the period of oscillation and the spring stiffness. To the left is the Tracker video and its data. The length scale is 0.70 meters. The system's mass is 0.402 kilograms, and I observed the system from the fourth frame at its equilibrium position to the final frame, and I used the y-axis, which was aligned with the fixed attachment point with the negative end pointing downward. To calculate the period of oscillation, I used the graphs generated by Tracker. The top graph shows the x position versus time, and the bottom shows the y position versus time. I specifically used the y position versus time graph, and I observed 5 complete periods as shown below and found that the last period's time was 8.262 seconds, and the average period time was calculated to be 1.6524 seconds as shown in red. From lecture, we learned that we can manipulate the period of oscillation formula to solve for the spring stiffness, which will equal 4 pi squared times mass over the period squared. When we sub in the correct values, we can calculate the spring stiffness to be 5.81 newtons per meter. Next, we can calculate the spring's relaxed length by looking at the system when it is at static equilibrium, which is when the spring and gravitational forces are equal to each other, resulting in a net force of 0 newtons. By setting the two forces equal to each other and solving for the relaxed length L naught, we can calculate this value to be 0.0219 meters. To create the computational model in this lab, I set the initial position given by Tracker, and the velocity was the zero vector since the system started at rest. And I advanced the time by 1/210 seconds, also known as delta t. Along with this, I defined the gravitational constant, the spring stiffness, and the relaxed length we calculated earlier. In the next section, I used Hooke's law to calculate L hat and the spring stretch, and lastly, I used the energy principle to calculate the kinetic energy and the spring and gravitational potential energies, which when added together allowed me to calculate the system's initial energy. Next, I updated the system's data iteratively. First, I calculated the spring and gravitational forces interacting with the systems, and next, I used the momentum principle in green to update the velocity and position to predict the system's motion, and in purple, I used Hooke's law to update the spring stretch. Lastly, I used the energy principle to calculate the system's change in energy by calculating delta K and delta U for both spring and the earth. After running the code in GlowScript, I obtained the change in energy versus time graph to the right, in which the kinetic energy is the blue curve, the gravitational potential energy is in red, the spring potential energy is in green, and the change in energy is in orange. Notice how the spring potential energy and gravitational potential energy are inverses of each other. Another key observation is that the change in energy is zero, which makes sense because the surroundings do no work on the system. Despite this, there is still an error in my model, specifically in the position versus time graph below, which uses the y position data. The computational model in blue greatly overpredicted the observed data in red because Tracker did not take the drag force into account and potential human error in how this data was tracked, but the graph and data have close similarities. After completing the lab, it is clear that the model system satisfies the energy principle because the change in energy is zero since there is no work done by the surroundings, and is also satisfied in the graph when the spring and gravitational potential energy have the same amplitude but are in different phases. Lastly, I estimated the period of oscillation using the X and Y data and used the same process as we discussed earlier. The average period of oscillation for the X data was 1.6904 seconds and the Y data was 1.6524 seconds, and although they were very precise compared to each other, they are very different in terms of how they are calculated. The X period was based on the spring moving left to right, and the Y period was based on the spring moving up and down. In conclusion, we used the energy principle and the momentum principle to analyze the spring mass system's motion, and we created a computational model of the motion to compare it to our own observations, which proved that both the energy and momentum principles are being obeyed. Thank you for watching.